In this video, we are going to go through one of the differential equations practical problems. So this problem is one where we have an object whose temperature is higher than that of the surroundings, and we are interested to find out how the temperature of this hot object is changing with respect to time. Eventually, the last part of this question basically requires me to find how much time is required for an object whose temperature is originally 5 times that of the surroundings to decrease to twice that of the surroundings. The first part of this question requires us to find out a differential equation that connects theta and t, where theta is the temperature of the hot object at time t. And at the beginning, we were given some information on how the temperature is decreasing with respect to the difference between the temperature of the hot object and the temperature of the surroundings. The plan when we went through the video hints was to note that d theta dt is proportional to theta minus theta naught, and eventually when we want to write down the solutions, we need to consider whether d theta dt is going to be positive or negative, and whether theta minus theta naught is going to be positive or negative. D theta dt is the rate of change of the temperature with respect to time. We know that as time increases, the temperature of the hot object is going to decrease, and it's going to get nearer and nearer to that of the surroundings. This tells me that d theta dt is going to be negative. At the same time, theta minus theta naught, the temperature of the object was originally hotter than that of the surroundings. So theta minus theta naught is going to be positive. So now we are ready to write down the differential equation. We know that d theta dt is proportional to the difference between the temperature of the object and the temperature of the surroundings. Okay, but the left hand side of this equation is negative. And when it comes to differential equation, and when we need to write down the constant of proportionality, we are used by convention to use a positive constant. So where k is a positive constant. Since the left hand side of this equation is negative, the right hand side of the equation also has to be negative. However, k is positive, theta minus theta naught is also positive, so in order for this equation to be valid, we need to write down the negative sign. So that's the answer to the first part of this question. The second part of this question requires us to find the general solution of the differential equation, and in fact they want us to show that it can be put into this particular form. Basically, we need to solve for the differential equation that relates d theta dt and theta minus theta naught. And the hints were, what we need to do was to separate the variables and to know that in the equation that I need to show, k is going to be the constant of proportionality. So the solution goes that since d theta dt we have is equals to negative k theta minus theta naught. In order to solve the differential equation, I need to separate the variables. So in this case, the variables are theta and t. So I will bring all the theta to the left hand side of the equation. In this case, we are left with a constant on the right hand side. And then I integrate both sides of the equation with respect to t. And I have integrate 1 over theta minus theta naught with respect to theta is equals to integrate negative k with respect to t. And this will give me ln of theta minus theta naught is equals to negative kt plus c. Note that there's no modular sign for the ln because theta minus theta naught is positive. And then this implies that theta minus theta naught is equals to e to the power minus kt plus c, which is equals to a times e to the power of negative kt, where my a is equals to e to the power of c. So therefore, my theta can be expressed in the form of theta naught plus a e to the power minus kt, shown. The last part of this question basically gives me information on the temperature of the hot object at different times, and I'm supposed to find the time taken for the temperature of the hot object to be twice the temperature of the surroundings. So the plan was to make use of the general solution and given information to find a particular solution, or in fact to find the values of the various constants, and eventually sub in theta equals to 2 theta naught to find t in terms of t. And in the hints, we gave you the values of the various constants that I need to find. We have theta is equals to theta naught plus a e to the power negative kt. The first information tells us that when T is equals to 0, the temperature of the object is 5 times the temperature of the surrounding. So theta is equals to 5 theta naught. And that gives us 5 theta naught is equals to theta naught plus A e to the power of 0, which implies that A is equals to 4 theta naught. Second piece of information, when T is equals to big T, theta is equals to 3 theta naught. And that gives us 3 theta naught is equals to theta naught plus A, but A is 4 theta naught e to the power of negative k big T. That implies that 4 theta naught e to the power of negative k big T is equals to 2 theta naught. Divide theta naught on both sides. Now I get e to the power negative k big T is equals to half. And if we apply ln on both sides of the equation, I end up with negative kt is equals to ln half, which is equals to ln 2 to the power negative 1, which gives us negative ln 2. So therefore, my constant of proportionality k is equals to 1 over t ln 2. Now, to find the temperature when theta is equals to 2 theta naught, I make use of the equation that I found. I sub it into the equation, but with the values of A and K, I get 2 theta naught is equals to theta naught plus A, which is 4 theta naught, e to the power of negative k, which is 1 over t ln 2 multiplied by the time t. Objective is to find the time t. So this implies that 4 theta naught e to the power of negative 1 over t ln 2 multiplied by small t is equals to theta naught. And this gives us e to the power of negative 1 over t ln 2 multiplied by small t is equals to 1/4. Applying the ln function on both sides of the equation, I get negative 1 over t ln 2 multiplied by small t is equals to ln 1/4, which is just equals to negative ln 4, and then I get 1 over big T ln 2 multiplied by small t is equals to ln 2 square, and I get 2 ln 2. Dividing both sides by ln 2, this is what I get, and so therefore eventually I found that time is equals to 2 big T. And that's our final answer. When time is equals to 2 big T, the temperature would be twice the temperature of the surrounding.